Hi, and welcome back to the CCNP route training. We're actually going to be looking at more advanced topics in EIGRP. So if you thought that you got a lot before, there's even more now. There's a lot of functionality. EIGRP is a very simple protocol, but there's still a lot that you can do with it. So we're actually going to review that in this particular lesson. So just as a summary for what we're going to be covering, we're going to look first at neighbor authentication and what that means, default routes, how to accomplish route summarization, the functionality required in route filtering. There are several methods we'll explore, EIGRP stub routing, which we'll actually implement on router 5 in our lab, and then finally we're actually going to step through the configuration of advanced EIGRP lab exercises in our topology. So let's begin with neighbor authentication. One of the things that is a constant in network security is the simple adage, trust no one. If the routers in an EIGRP topology can be peered with any router that it's simply configured to peer with, how do you know that someone isn't putting in an unauthorized device to be able to create some sort of problem? That's really the idea behind neighbor authentication. So we want to actually be able to step through the building blocks of EIGRP neighbor authentication, how to configure it, and then how to verify that it's actually in operation the way that's intended. So let's begin with, what is neighbor authentication and how does it operate? What does it do? What does it not do? You can obviously look out here to the left. We have, in this particular case, a key that's configured on each one of the devices with the string myEIGRP key, and they have to match in order for the relationship to come up. So let's just understand what this particular feature does. It restricts what devices may form neighbor relationships. If the string or key does not match, the neighbor relationship will not be established. There's also an authentication of all messages sent between the configured keys, whether they're hello messages or update messages. All those messages have to have the required key to be accepted. And it actually ultimately prevents denial of service type of attacks. That's what authentication can provide. But that can lead some people to believe that, oh, all the traffic is actually being encrypted. And that's not true. None of the traffic's encrypted. It's sent back in the clear. The only thing that's protected is the key that's used to authenticate between neighbors. So there's no encryption, there's no type of data privacy involved with this at all. There are probably some sophisticated ways to do that using tunnels and IPsec encryption, but far beyond the scope of what we're talking about. So understand what neighbor authentication does and does not do. So how does EIGRP neighbor authentication actually function? Well, it's interesting to begin with that open text mode is not supported. In a number of other protocols, it is an option, but not in EIGRP. Only MD5 is used, and it is used to ensure that no information is transmitted in the clear. MD5 creates a 128-bit hash that cannot be easily broken. The configuration elements are very similar to the way they are in routing information protocol, we'll talk about later. A pre-shared key is configured on each one of the neighbors, and it's performed on a per interface basis. For instance, you could just assume here that the VLAN 12 interface is the one that the key is being used on. So you can put a authentication key requirements for that interface and yet not require it on the frame relay interfaces or vice versa. It can be done on a per interface basis. So very simple and straightforward to understand, and even more straightforward to configure. Configuring it begins with defining the pre-shared keys. Now you can look here, the syntax for the first part, namely the key definition, is pictured here to the left, using the keychain and then the name of the keychain command in global configuration mode. In this case, you can actually create multiple keys using integer values, key 1, key 2, key 3. It's very similar to what you'd see when you create encryption keys for wireless access points and so forth. But the pre-shared keys are defined with the key string text, which you actually see here under key 1, key string myEIGRP key, not an imaginative name, but very simple and straightforward. And that's under keychain configuration mode. You go to keychain EIGRP, and then you have successive levels of that configuration that you do. You can actually have differing lifetimes defined for each key. Accept lifetimes and send lifetimes if you wanted to overlap the way different keys were being used so that any problem with someone trying to insert or maybe actually having possession of that key, that can be avoided. And the keychain names are locally significant. In other words, you could actually have a completely different keychain name on R3 that isn't the same as it is on R1. The only thing that's critical is to make sure the key strings match. I think it's good practice to use the same names, but that's not the critical point here. So define your keychain, define your key string, and make sure that they match. And one thing to keep in mind is, and you can miss this in the configuration because I've done it before, is, for instance, my EIGRP key and my EIGRP key space will not match. And you may not be able to see that until you actually do a show keychain and actually see the quotes and the fact that there's a space after it. So keep that in mind, it could trip you up. Applying the configuration to the interface once you've defined the keychain is also very simple. It's applied using the IP authentication keychain, EIGRP. You have to put in the correct autonomous system number and the keychain name. It's actually defined down here in the text. And even though there's only one mode that's supported, you have to specify it. If you put in the IP authentication mode keychain EIGRP 100 and you don't put in the IP authentication mode command, it will fail. It will consider it as not operational. So both of those commands must be part of that. Keep in mind the syntax. Once you've configured your neighbor authentication, you need to make sure it's operational. Obviously, if your neighbor relationships don't come up across that particular interface, you may have a problem. But you'll find these commands very helpful. Show IP EIGRP interfaces should show active peers. In other words, non-zero. It should list the same number of peers that you had prior to configuring it. Show IP EIGRP neighbors should show all of the neighbors in the neighbor table that you expected to see and had previously before you configured authentication. Show keychain will list the configured keychain and valid lifetime settings, and as I explained before, if there's a space that you accidentally put in the particular text, it will show that within the quotation marks. Debug EIGRP packet can display neighbor exchange messages. You can see, for instance, if something's being rejected, you'll be able to get a reason why, and that may help you to troubleshoot it. And it's also helpful to set NTP on the different routers, because sometimes if the clocks are not synchronized, there can be interesting reactions that the equipment makes in that regard. So try to make sure that everything's synchronized from a time standpoint. Default routes are actually of particular importance in just about every network. So we want to be able to take a look at that within the context of EIGRP. We want to first understand what default routing is, what the purposes are, and then there are two methods in EIGRP for configuring that. There's redistribution of a static route to 0000, which is very common. Then there can be a configuring a default network. And then finally we'll look at how to verify that that's operating as expected. So what is default routing? Why in the world would you want to do it? There are a couple of reasons. First, it communicates the path to other networks in host routing. If you remember, you just have a host machine. It will either send devices on its own network or it'll send it to the default gateway. That's essentially the same thing as having a default route. If you do the route print command from your command line, you'll see the default route. So it communicates the path to other networks in a host routing environment. It also designates the path within an enterprise network to one, or in some case more, internet-facing routers. So it communicates how to get to essentially the internet gateway, whether it's defined locally in a branch office, because that sometimes happens, or whether it's at a headquarters. Either way, it communicates that throughout the network. And if there's only one path in and out of a particular network, for instance, a branch office or home office, it creates very simple routing because there's only one point in and out of the network. You can just do a default route and it'll send everything out correctly. So some very simple ways that default routing can be very helpful. So what exactly is the mathematical significance of the default route? Well, it's actually the polar opposite of the broadcast address, which is 255.255.255.255, where it's saying everything on the network should get this. It's essentially saying that the most general network possible, any network, is what the 0000 essentially stands for. 0000/0, or with the mask of all zeros, essentially says match everything. And what it means is that if the particular network does not exist in the IP routing table, go to that particular destination. That's why no one would want to put all of the internet routes in a locally facing internet router unless you're an internet service provider, so the default route just makes that very simple and clean. So that's why default routing is so helpful in so many instances. So again, I mentioned there are two ways to do this in EIGRP, and the first of those is redistributing a static route, essentially to network 0000. And it's actually very simple. The first step is to create the static route. And you can use one or more of these routes. For instance, if you have multiple exit points to the internet, you can actually have several configured, but you essentially do the IP route 0000, whatever the next hop router is, and whatever metric or administrative distance you want associated with that route. Lots of times in my equipment, when I configure the default route, I will give it an administrative distance of 2 just because I want to make sure that nothing interferes with that. I've had very interesting experiences sometimes propagating default routes within a lab and then essentially not being able to get to it because it overrode the default route. But if you want to do multiple routes, in other words, you could say that the default route to this particular device would be primary, and then if that's not available, go to the other one. You can do what are called floating static routes. You do, for instance, the default route with an administrative distance of 2. That would be your primary route. If for some reason that's down, you could do another one that simply has the same thing but with an administrative distance of 250, which means it would only be used if the other one was not available. You can actually create a whole hierarchy with that. So you have to define the static route in the device that's going to be doing the default route propagation. Then once you've done that, in this case we're going to be doing it on router 4 facing the ASA firewall, you have to redistribute it into the protocol. And again, redistributed routes in EIGRP are going to have an administrative distance of 170 and be designated with the DEX, meaning external. So you can do redistribute static to make it very simple, especially if there's only one static route defined. Or you can use the network 0000 command. I'm a fan of doing the redistribute static, but that's pretty much all there is to the process of doing it this way, and we'll actually create that in our lab in just a moment. The second method for configuring a default route in EIGRP is to configure a default network. Usually you'll put this on a primary device. It's typically a loopback interface, but that particular network has to be known by all the other devices in the EIGRP routing domain, or it will not show up in the EIGRP routing table as the gateway of last resort or candidate default route. On whatever router that you're using as the transit point, for instance in our lab we'd be using R4, you issue the IP default network and then whatever that network is command. And then you will notice that in the IP routing table it'll be flagged as a candidate default route with the star, the asterisk, and that'll be your clue, as well as seeing gateway of last resort. I don't happen to prefer this method, but it is another way to do it. So keep that in mind. That's also a valid way to approach this same issue. So how do you verify this is working? It's actually pretty simple. Is there a default route in the routing table or not? Show IP EIGRP should list the route to 0000. Again, administrative distance of 170 and the DEX designation. If you want to, you could do show IP route 0000 and it'll do the same thing. It's a lot more specific. Execute the show IP EIGRP topology and you can actually look at the entire topology table and actually see if the network is in there. And then finally, you can list out show IP EIGRP topology with the 0000 network, and it'll give you all kinds of detailed explanations. The easiest way to make sure this is functioning is, number one, is it in the IP routing table? And number two, pick a publicly routable IP and try to ping or trace to it from within the network. If it operates correctly, then you know routing is working both incoming and outgoing, and that's probably the best verification for knowing that it's functioning correctly. Now later in the lesson we actually have a spot designated for configuring the default route, but since we've just gone over it, I figured no better time than the present. So we first want to go to router 4 because this is the internet facing router. And again, since it's our terminal server, the login process is just a little different than it is in our other devices. So there's already a default route configured. Notice here it's statically configured. Administrative distance of 2, like I had mentioned before. So the way to be able to do this, router EIGRP 100. I'm going to open up a session to router 1 as well. Show IP route. Notice it says gateway of last resort is not set. There's no default route, and that's also designated by the fact it doesn't appear in the table anywhere. So let's go back to router 4. We need to use the redistribute command. You can see that when you do that, there are all sorts of choices. We're going to do redistribute static. There are all sorts of things that we could do, like defining the metric. We'll just leave it at that. Let's redistribute static. Now let's go back to router 1. Now look here. Gateway of last resort is, and that's to router 4, to that network. And it is listed here, just as it's expected. So we'll do a ping test, 216.145.1.2. This particular case, we have ICMP blocked at our firewall. But you can see it's correctly operating within the table. So that's the, and also the fact that we're able to even access these devices tells you that it's actually working. So that's actually all there really is to the whole concept of creating a default route within an EIGRP environment. So let's deal with route summarization in EIGRP. And some of the questions come up, we're going to actually address this, is why would you want to summarize routes to begin with? We'll look at that. We'll also look at choosing where to summarize, because in EIGRP you have a multitude of choices. How to configure summary routes, and then how to verify summary routes. Now the question begins with, why would you want to summarize routes at all? And there's actually the graphic here, I think, very well illustrates it. Notice all of these networks that would be propagated by the router on the left to the router on the right. Quite a few routes. But all of those routes can be summarized in a single statement. So instead of propagating all of the 192.168.1 through 15 routes, a simple 192.168.00/20 can serve the same purpose. When you think about the size of routing tables on the internet, this is one of the reasons why IP version 4 has managed to still stay in existence without crashing and burning on itself. So just some positive aspects of route summarization. First, you're reducing the size and scope of routing tables, not just on the internet, but within an enterprise. The fewer routes that have to be processed, the faster things can go, because it's not placing a burden on the CPU. The other thing it does is it shrinks query scopes. One of the things about EIGRP queries is if it's going to, one neighbor is querying another for a route, it then will query its neighbor and its neighbor and its neighbor, kind of like ripples in a pond. If it has to go through 27 routers to make a query, you could see where the process of going all the way up and all the way back to all the different neighbor routers and this cascading effect could take quite a bit of time. When a summary route is configured, only the router that's summarizing and advertising that route gets the query. And that can really shrink the scope of how far these queries have to travel. And ultimately, another thing is because summary routes carry the best metric, administrative distance can be much lower. Now, a couple drawbacks to using summary routes is it sometimes can result in less than optimal routing for just a variety of reasons. And another thing is it can create packet discards. In other words, if the network that's within the summary, for instance, has gone away and the summary is still being advertised because some aspect of it is still up, then packet discard may happen and it make troubleshooting just a little more difficult. So those are some things to keep in mind, both benefits and drawbacks to route summarization. Another thing to really take into account, and this is more of a design discussion, is choosing where you're going to summarize. Good network design uses summarization wherever possible. If your IP allocation scheme is planned well and done correctly, summarization can be very, very simple, very much like the picture to the left. If the IP addressing was designed in such a way to be able to summarize that easily, that's great design. And specific areas of the network may lend themselves to summarization. For instance, in the data center, there could be a whole range of addresses that are being used. All the individual addresses don't need to be advertised. If there are, for instance, 16 networks, just advertise one prefix. A wide area network can have a variety of addresses. The network core, campus locations, there are all sorts of ways to be able to use network summarization in specific areas because it lends itself to that very well. So select summarization points carefully and then make sure you calculate the routes correctly. For instance, using the example to the left, if, for instance, this prefix was /19 instead of /20, there'd be networks that would be included that may not actually be there. So be very careful when you calculate it out, that you've actually calculated it out the best way possible. Configuring summary routes is very simple. It's done on a per interface basis, and it's done with the command IP summary address, EIGRP, the autonomous system number, whatever the network is that is going to be advertised, the mask with which it will be advertised, and then optionally an administrative distance. The default would be 5, but you could put others in there if you want to. Once you've done that, the neighbor relationship will drop because a summary address has been configured and it's changed the way the topology will operate. On that particular router, there will be a summary route to null 0 created in the IP routing table under the EIGRP process, and you'll actually be able to see it. It'll say route to null 0, such and such is a summary. More specific routes in the neighbor routing tables will be suppressed in favor of that summary route. So, for instance, using this example to the left again, all these 15 routes that are listed will not appear in the routing table of the router to the right. They will all be suppressed in favor of the summary route. And you could do multiple summary routes per interface, but you also want to be careful to make sure that there isn't overlap as well, but a very simple thing to configure. To verify summary routes is again a very straightforward process. Show IP route EIGRP, you should see the summarized route. Moreover, you should not see the routes that have been summarized. Show IP route and a specific prefix should actually list out the details. Show IP EIGRP topology should do the same thing, only list the summary route, not the other ones. And then on the originating router, make sure that you do a show IP route and see that there is a null 0 interface pointing to that. That should be another aspect of understanding and verifying how your summary routes are operating. Default routes, route summarization. What about route filtering? There are a variety of reasons why you'd want to filter out particular routes. You might not need every single branch to have a route to every other branch because they don't need that reachability information. Information is flowing from those branches back to the headquarters in a hub and spoke fashion. There's no reason to clog the routing tables with that. So you may want to filter out for those reasons. There's a variety of reasons, but there's a lot of ways to do it. There's definite tools in your bag as an engineer to be able to do that. You can do very simple filtering with access lists. You can filter using prefix lists. You can increase the metrics if you want to make another route less desirable using offset lists that essentially pads the metric. You can do more advanced filtering using route maps, and then finally you want to be able to actually look and make sure that the filtering is working the way that you intended. So let's start first with just a very simple filtering process. Now keep in mind that all of these route filtering processes that we're going to use in these first 3 examples are going to be based on distribute lists. And distribute lists can use access lists, prefix lists, and route maps. So in this particular case, you see pictured here that R1 wants to allow advertising of the 10333, but deny 192.168.30. And actually, it's the other way around. It'd be R3 advertising back out. Actually, it could be either way, but the process is essentially the same. First, you have to remember some just general principles regarding how access lists operate. First, processing is top-down, much like it is in programming. It starts with the first line, then it goes to the second line, and so forth and so on. If a match is made, processing stops. So if the first entry is matched, it just stops. It's not going to go through the rest of them. If the third is matched, it's not going to go through the succeeding ones. It's a very simple match and then response. The actions of an access list are permit and deny. If you're actually doing packet filtering, it's whether to allow it or to discard it. In the case of filtering, it's whether to allow it or not allow it. At the end of an access list is an implicit deny all. I think it's a good process to put that in manually so it's a reminder. Access lists use wildcard masks, much like EIGRP masks. It's the polar opposite or inverse of subnet masks. If you're not sure how to do the math, just take 255, subtract it from the subnet mask, and you'll get the wildcard mask. Another thing about access lists, and standard access lists are what are used in route filtering, they can be named or numbered. Access list 1, permit, subnet, wildcard mask, etc., or a named one. So just some general access list principles. Now, when you want to use an access list for route filtering, again, as I mentioned before, it's going to use standard rather than extended lists. It's just going to be a simple permit or deny, network, and mask. Now, when you're doing these, make sure you place more specific entries before more general ones. If you put the general one first, they'll in an immediate match and the specific ones won't be listed. So always go from specific to general when you're listing things. Make sure you apply the access list using the distribute list command under the EIGRP routing process. The syntax is very simple. Access list, the number or name, permit or deny, the prefix or network, and the mask. That's access list definition. For the distribute list, you put in distribute list, the number or the name of the access list, in or out, because you can filter incoming updates or outgoing updates, and then whatever interface is involved. Prefix lists have a great deal more functionality than access lists. Access lists essentially just talk about what IP address to match. You cannot really specify what mask to match. So it allows for the ability to be able to match route prefix and subnet or prefix length and mask. Like an access list, there are essentially two actions, permit or deny. Permit means the route's matched. Deny means the route's not matched. This isn't like the permit and deny as to whether it will allow a packet. Another very strong part of prefix lists is you can actually specify mask lengths. The LE means less than or equal to, meaning here's the number of bits to match, less than or equal to this. Greater than or equal to is the opposite, and you can actually use them together to specify a range. And just like the access list, you can apply it using the distribute list command. It'd be distribute list and then the prefix list and then the syntax for that. Here you can see the prefix list syntax. It's prefix list and it's named. It's not numbered. Permit or deny, the prefix length, prefix slash length, then later less than equal to, greater than equal to, and the values that are involved. For instance, if you wanted to specify all 10 dot addresses, you could use 10.0.0.0 greater than or less than and equal to 32, less than or equal to 16, and it would be a variety of different ways that you can match those. That it can get quite complex. And then distribute list, you'd put it in and match how it's being used in what interface. If you desired to be able to create a higher metric for one particular interface without changing the bandwidth or delay commands, you can actually use the offset list to actually increase the metric. And this actually uses standard access lists to match routes or prefixes. This is permit. The offset lists can increase the integer value. They can be applied to either incoming or outgoing networks on specific interfaces. They can, and ultimately when you do that, you change the metric, both the reported distance and the feasible distance. So you can see where this could be particularly useful. If you use an access list of 0, for example, it means that it will match all networks. And applying the list for offsets will reset the neighbor relationship as well, so keep that in mind. The offset list is actually very simple syntax. It's offset list, the access list number or name, in or out, whatever the offset value is, and it can be from 0 to 214.748.3647, very large number. And offset lists are configured in EIGRP router mode, so offset list with the syntax we talked about. Route maps are the final way of being able to use route filtering technologies. It gives you more flexibility, not as much in EIGRP as in other routing protocols, but it's still there. There's a variety of manipulation and route functionality that can be performed. There are sequence numbers in use. In other words, you could do 10, 20, 30 to be able to create a whole list of things in a route map to evaluate and execute. And there are two aspects to route maps. There's match and set. Match specifies the criteria for choosing a particular route or subnet or interface. And it can match an IP address, it can mention the next hop interface, the specific interface, route metrics, and so forth. You can also match route tags, which you can also set in EIGRP. Route types, MPLS labels out of scope, and then tagged routes. EIGRP can do that as well. Set specifies what actions to take. What's the metric? You can use an offset, kind of like the offset list, or you can just change the metric altogether. You can tag certain routes and then use those for redistribution later. And there are other values for set in route maps, but they don't apply to EIGRP. There's a lot more. For instance, you can set internal and external routes in OSPF. You can set all sorts of things in BGP, which we'll talk about later. But this is essentially the capabilities of a route map in the EIGRP protocol. So the route map syntax is very simple. It's route map, whatever the name of the route map is, permit or deny, then a sequence number, match and set, as we talked about, and then under EIGRP, it's distribute list route map, the name, and then whether it's in or out. So how do you verify route filtering is working correctly once you've configured it? First, if you're using access lists, do the show access list command. The access lists that you're using should have some incrementing value if they're matching what you intended. You could do show IP route EIGRP and make sure the routes that you're trying to filter are indeed missing from the routing table. If you're filtering on all interfaces, you can use the show IP protocols command and it will actually show you that there is a filter list applied. If you're just doing it on one interface, it won't show up in show IP protocols, but you will be able to verify it if it's on all of them. For prefix list filtering, do show IP prefix lists, and again, it's very similar to what's going on in the access lists. You can also use the show IP route EIGRP and make sure the routes you're trying to filter using the prefix lists are not there. For offset lists, do the show access list, make sure it's incrementing. Do show IP route EIGRP and look and see what the metric is and that it's actually incrementing the way you expected. For route maps, use all the commands we've talked about up till now, whether you were using prefix lists or other aspects in the route map. Actually make sure they're doing what they're intended to do. One of the distinctive features in EIGRP is the ability to not only load balance across multiple equal cost links, but also the ability to be able to do unequal cost load balancing. So one of the things we want to do is take a little bit of at least a brief look at it. It's very simple to configure, but want to understand the dynamics, understanding how equal and unequal cost load balancing works in EIGRP, how to configure it, and then verify whether or not it's working. Now to begin with, equal cost load balancing, to understand both the concepts, is the idea that if metrics are equal for more than one route or successor in the EIGRP topology and IP routing tables, the protocol will use them equally, and the default is up to 4. Obviously, there are more that can be configured. If, for some reason, there was a desire to have more than 4 routes, it would just simply be adjusted using the maximum paths command under EIGRP. However, the distinct feature we want to take a look at is unequal cost load balancing. As you look to the graphic to the left, on the dark blue arrow is the 10.3.3.3 route that we've been talking about a lot. The feasible distance is 156.160, and it is preferred. When you look at the feasible distance of the other route on the frame relay network, it's 106.39872, a great deal larger. So under normal conditions, that wouldn't even be considered. It would be the feasible successor, but it would not be actively used. However, there's the ability to use a multiplier value, an integer value between 1 and 128, to be used to allow a route with a higher metric to be available and usable. If the variance is at 1, then it means don't use unequal cost load balancing. But if you want to be able to use it, you can adjust. In our particular lab environment, because of the vast difference between the metrics, variance of 70 is necessary to get both of them to work, but then they will both appear in the IP routing table. So configuring it's very simple. You go under EIGRP router configuration mode, and you enter the command variance, and then an integer between 1 and 128 to be able to designate the difference, the multiplier value, to allow the larger metric to be considered another available route. So how do you verify it once you've configured it? You can do the execute the show IP protocols command, and the first thing to do is to look, and it will actually say what the EIGRP variance variable is. If it's set at 1, it means that only equal cost load balancing is used. But if it's anything greater than 1, then it's saying use unequal cost load balancing depending on the difference in the metric. You can also do show IP route EIGRP and show IP EIGRP topology and verify the existence of the second unequal route. The show IP route is going to be the most definitive because you can actually see where it's listed in the routing table, the prefix, then both the routes with the unequal metrics that allows that to be used actively as part of the EIGRP topology. Another very important and popular feature to be able to maximize and essentially optimize bandwidth in EIGRP networks is the stub routing concept. We're going to take a quick look at understanding what stub routing is, how to configure it, and then verify that it's operational. So what is EIGRP stub routing? We actually have the graphic to the left pictured showing router 5, which we'll configure as an EIGRP stub, and you notice there's only one instance, one interface in and out of the network. So what this particular feature accomplishes is if a particular device is not being used as a transit device to other EIGRP networks, there's no need to have a full routing table. You notice, for instance, R2 is a transit device. It has active routing between router 5 and router 1, for example. Frequently, when you have branch offices, it's typically a hub and spoke topology. There's no need for anything other than stub routing. It also will limit the scope of EIGRP queries. It'll take that traffic down. And the stub router depends on the hub router for sending whatever appropriate updates for the changes in its particular networks. And it can actually very simplify spoke configuration for these particular devices. Configuring it's very simple. It takes place on the actual stub router. There is no change in the configuration of the upstream router. The router EIGRP autonomous system command is necessary to start the process. The network command should be executed just for the link to the upstream router, in this case between R5 and R2 on the VLAN 25 interface. And the stub process is started using the EIGRP stub in EIGRP configuration mode, and then there are several options: connected, summary, static, redistributed, and receive only. Connected means it will advertise all of the connected networks upstream to its hub router. Summary, it will just simply put summary routes. Static, it will include whatever static routes are included. Redistributed, self-explanatory, and then receive only means it's just going to receive routes. It's not going to actually send any of the rest out. Verifying that it's operational actually requires execution of the IP neighbors command. If you execute the show IP EIGRP neighbors command, it's going to show the presence of the hub router. If you do show IP route EIGRP on the stub router, it's actually going to show all of the routes that you expect. But on the hub router, if you do show IP EIGRP neighbors detail, it will actually clearly identify it as a stub router. And then if you do show IP route EIGRP and look and see on the hub router if all the routes coming upstream are as expected. So while we've done some configuration, we actually have some other things we want to do as part of the advanced lab that we're going to be doing. We're going to review the configuration commands we're going to be using. We're going to apply those advanced commands to the EIGRP routers and then verify them. Now first we're going to do neighbor authentication with the keychain command that we talked about. We'll use a pre-shared key. We're going to apply that using the two commands. Remember, the keychain and the mode command both have to be under the interface for it to function. We're going to actually put that between the frame relay connections only, and we'll be implementing that in just a little bit. We'll also create a default route propagation. Actually, we already did this. We created the default route propagation on R4, injected it using the redistribute static, and you notice that it appeared in the IP routing table on R1. We're going to use summarization on R2. We're actually going to suppress the /32 loopback address and actually summarize it using the summary address command. For route filtering, we're actually going to filter out the 10/2/10.2.2.2 network, which shouldn't be propagated anyway. We'll put that particular filtering in place using the distribute list and an access list. We could do similar filtering with the IP prefix list, but we won't include that in the lab. And then finally, we'll do EIGRP stub routing and the variance command as well for load balancing. We'll also be applying unequal cost load balancing on R1, as we talked about before, so that the frame relay and the VLAN interfaces will both be considered valid. That'll be using the variance command. We'll be applying EIGRP stub routing on R5. We'll strip out all the existing network commands except for the link between R2 and R5. And then we'll configure stub routing using the EIGRP connected, which will just take the simple connected routes and propagate them up to R2. So the configuration that we'll actually use on the routers, we'll use a pre-shared key of my EIGRP key simply between the frame relay networks and neighbors. The configuration of the default route's already been completed. We'll create the summary route from 10.2.2.0 from R2. We'll filter unnecessary updates. We'll configure EIGRP stub routing on R5 with R2 serving as a hub site router, and we'll also be configuring load balancing between R1 and R3. So now we're actually going to do the configuration that we talked about in the advanced part of our labs. We have routers 1 through 5 as part of this, and this under authentication is the first configuration we'll be doing. So we will, as you see, we have the keychain of my-key, and we'll be using my EIGRP as key 1. So we'll go to configure terminal. So let's try this again. It's key chain my key 1 key string. I'll go back and make sure we've got it correct because we don't want to have it work incorrectly. My key. Now we want to exit out of these. Now we want to go to our interfaces, which is interface serial 00/12, which is our point-to-point, IP authentication keychain, EIGRP 100. Now it's looking for the name of our keychain, which is my key. You notice when we do this, the neighbor relationship there will drop. And there we go. And it's come back up because we don't have the rest of that configured. But remember, we also have IP authentication mode, EIGRP 100, MD5. Now it'll drop again and not come back up. Now we need to do the same thing with serial 00/134, which is our multi-point interface. Okay, so now all of those are configured. Now we can go to router 2. Maybe we can just copy and paste now. Except it didn't like key string. And there we go. Now interface. I'll have to now interface serial 0/12. Now IP authentication keychain EIGRP 100. We'll copy and paste the name so it's correct. My key. Now IP authentication mode EIGRP 100 MD5. Now we will go and configure this on router 3. will hopefully have the syntax correct. Copy. Now, let's interface serial 00, IP authentication, EIGRP keychain, EIGRP 100. My key, IP authentication mode, EIGRP 100, MD5. Go to router 4, which is the last one on our frame relay network. Go back to our configuration. Interface serial 0, IP authentication, EIGRP keychain, EIGRP 100, my key, IP authentication mode, EIGRP 100, MD5.
So just as a way of wrapping up the lesson, let's actually go over a couple of terms that you should know. MD5 is the Message Digest Algorithm 5. This is a hash function that creates a 128-bit hash value and is used by the EIGRP process with neighbor authentication. Route summarization is actually the process of taking a larger number of contiguous networks and reducing them in a reduced form, usually 1 or 2 statements. Route filtering is the process of selectively removing routes from the routing table, or possibly the routing process. A distribute list is a route filtering method that makes use of access lists, prefix lists, and route maps in order to be able to reduce the routing table, removing routes. An offset list specific to EIGRP is the act of adding integer values to a route metric in order to influence routing metrics and actually to increase the metric. And a stub network is a reference to a type of network with limited entry or exit points, usually only one, in which limited routing capabilities may be used. This actually takes advantage of the EIGRP stub feature. So what did we cover in this lesson? We covered neighbor authentication in EIGRP, default routes, route summarization, how to filter routes in EIGRP, EIGRP stub routing, and configuration of the advanced EIGRP lab exercises. Thank you for your kind attention, and we will talk to you again soon.